All right, we are going to be looking at how to use rotations or revolutions in a 2D plane to end up generating a solid that we can find the volume of. And you can see here a demonstration of what that's going to look like. So you'll have a curve in the XY plane. You're going to revolve that curve around an axis, and then you're going to end up generating a three-dimensional solid. So let's look at an example here. Find the volume of a solid of revolution bounded by the graphs of f of x equals 1, and x equals 4 rotated about the x-axis. All right, I'm going to go ahead and explain what we're doing as we do this example. So I'm taking this piece right here, and I like to kind of draw a reflection over the axis where I'm revolving. And then I like to draw in that revolution, like so. All right, so if you notice, this is a disk. We're using disk method here. This is a disk, and you could do this multiple times. Like right here, this would be the disk that goes around this way, right? There'd be a disk over here. And so in order to find the volume, we need to add up the disks from x equals 1 to x equals 4. Well, we're going to add up the thickness, which is going to be our dx, because that's going to be what we call our width of our disk here. And then since it's a disk, I know that pi r squared is going to find me that area, and then multiplying by that dx piece is going to find me like a very baby thin volume, if you will. And then I want to add up all of those volumes along that interval. So let's think about how we're going to do that. I'm going to have a pi r squared dx, and then I need to add all of those up. Well, if you remember, what we do in calculus is we're going to then integrate from 1 to 4 pi. Now I need to figure out what my radius is here, dx. So my radius is my distance between my function and the x-axis. So it's just going to be my function squared, because in this case, again, r is equal to your function value, and that's what we're revolving around to make those disk pieces. All right, the expansion of x squared minus 4x plus 5, I'm going to take this pi out here, is x to the 4th minus 8x cubed plus 26x squared minus 40x plus 25 dx. And that's if I multiplied x squared minus 4 plus 5 times itself twice. This would be my full expansion. That means I'm going to have pi times 1/5 x to the 5th minus 2x to the 4th plus, unfortunately, 26 isn't divisible by 3, so 26 thirds x cubed minus 20x squared plus 20x, and I'm evaluating that from x equals 1 to 4. I plug in 4 into this whole polynomial to the 5th power. I subtract, plug in 1, and we end up getting 78 over 5 pi. And again, that's the volume of the solid that's going to be generated. Maybe it's like a table, right? Like with that being the top and then like that being the bottom piece right there. So that's the volume of that solid piece. All right, again, this is going to be the disk method, because think of it as like a quarter, okay, or like a frisbee, but even smaller, like more like dime size discs to quarters, kind of like lining up along your axis as if the axis went in between them. And then notice this is what we did in order to find our volume, is we added up all of those little mini disks from A to B. All right, use the disk method to find the volume of the solid of revolution generated by rotating the region between the graph of f of x equals the square root of x over the interval from 1 to x and the x-axis. So let's go ahead and look at a graph of what this function would look like. It's just our beautiful square root function. Again, I'm going from 1 to 4. And I'm revolving that around the x-axis. So I, again, like to kind of draw in that reflection piece and then what a disk is going to look like there. All right, so that disk has a thickness of dx and a radius of f of x, which is the square root of x. So to find the volume, I'm going to integrate from 1 to 4, pi r squared, square root of x squared dx. Now this one is not nearly as yucky. The square root and the square do end up canceling, and I'm going to bring my pi outside. So I have pi. The integral of just x is 1/2 x squared from x equals 1 to 4. I'm going to pull the pi over 2 here. 4 squared is 16 minus 1 squared is 1, so I get 15 pi over 2. All right, one more example for us here. Let R be the region bounded by this g of y function and the y-axis, and I want to go from 0 to 4. So let's go ahead and graph this. Sometimes I find it easiest to think about this as if this was x equals this function, and so I squared both sides. So this is like y equals 4 minus x squared is that relation, but it's just like the square root function. So I'm going to have, like if this was all of y equals 4 minus x squared, I just have the positive side, so the positive x's. So I'm going to just have this. And I want this region bounded by this function in the x-axis over the x-axis, so I'm revolving this way, and I want that to go from 0 to 4, which makes sense because here when I have 0 for x, then my output is 4. So that makes sense here. I'm taking this and I'm like revolving it that way. So these disks, right, are going to look like this. So now their thickness is dy, and again, I would have like multiple of these. Almost like a bullet shape, if you will. All right, so just one of these volumes is pi r, oh, well, that's g of y squared dy, and then I need to add all of those up from y equals 0 to 4. All right, pi comes outside. The antiderivative of 4 is 4y. Antiderivative of y is 1/2 y squared. And I'm doing this from y equals 0 to 4. I have 16 minus 8 minus 0. And so I end up getting 8 pi.